Okay. All right. Let's review a little bit what we talked about last time so that we can continue. Why is it important to do fat characterization? All right, Dora? What's that? For nutrition labeling of what exactly? Okay, so saturated fatty acid, trans fat, and there's something else that is on the nutrition label, Caitlin. Cholesterol, very good. What else do we care for? All right, I'm gonna go with Maisie in the back. Shelf life stability, oxidative rancidity, and hydrolytic rancidity. Yeah, what did you want to say? Do you want to say shelf life? Anything else?
You say sensory aspects.
Yes, the sensory aspect, palatability, mouthfeel, taste. Let's see, checking Madison. Effect of processing, absolutely. So let's go through all of that bit by bit again as a reminder. So nutrition labeling, saturated versus unsaturated, trans fat, cholesterol. These are on the nutrition label. Shelf life, oxidative rancidity, and this is a concern when we have a lot of polyunsaturated fatty acid. So the type of fat can also impact how fast the lipid is going to be oxidized during shelf life. Hydrolytic rancidity, that whatever is in there that's going to cause the triglycerides to break up. So if we have lipases, for example, so the enzyme lipase can be native, endogenous, present in some, let's say, oat. Oat flour has high level of fat, high level of lipase, high level of lipoxygenase. So oftentimes processing of oat involves heat treatment to inactivate the enzymes, so we don't end up having hydrolytic rancidity and oxidative rancidity. This is very common in oat processing, for example. Hydrolytic rancidity can also happen during deep frying. Like I said last time, the deep frying potatoes, they're high in moisture, and then you have heat, triglycerides are going to break up into fatty acids. That's hydrolytic rancidity. Whenever you end up having free fatty acids, that is hydrolytic rancidity. When we develop ingredients, so for example, olestra, which is an ingredient substitute for fat, basically it's sucrose esterified with 6 to 8 fatty acids. It won't be digestible, so it will not contribute to calories. Another time we form mono and diacylglycerols. Sometimes we form new types that are for emulsification purposes that have short and medium chain triglycerides. These will have less than 9 calories when they are consumed in our body due to the fact that they have shorter chain, fatty acid chain. So that is something for consideration. And then processing. We talked about potential production of trans fat, and this happens when you're doing hydrogenation to saturate your fats, but if it's incomplete, instead of forming cis configuration of saturated fatty acid, trans configuration can be formed, and this is something that we don't want. So hydrogenation, impact of incomplete hydrogenation might result in trans fat. Deep frying, like we talked about, the breakdown of triglycerides into free fatty acids, and always free fatty acids are more prone to oxidation than triglycerides. So they are more prone to get oxidized faster. You have faster reaction rate when you have free fatty acids. So in deep frying, we don't only cause the formation of free fatty acids by hydrolysis, but we also cause oxidative rancidity as well over time. That's why the oil, frying oil, is checked to see how many times you can reuse the oil before it is really bad, causing off flavors and health concerns as well. So refining, we talked briefly about refining. So I gave you the example of virgin olive oil. And in virgin olive oil, meaning the oil was produced and it wasn't refined, because you want to keep the characteristic flavor of olive oil. But usually oils are refined before they're used, especially for deep frying, because you want to get rid of all free fatty acids. You don't want free fatty acids in your oil that's going to be used for high temperature processing. So the refining process is basically adding an alkaline, mostly sodium hydroxide, that will react with your fatty acid to generate soap. And then there is centrifugation step to separate soap and water from oil. So that's your refining step. And to test if the refining has been done properly, you measure degree of free fatty acids before refining and after refining. Make sure that you have eliminated free fatty acid content. Winterizing is another processing that they do to kind of clarify the oil. So you have waxes in here. And if you reduce the temperature of the oil, the waxes are going to crystallize sediment and fall out of the oil. Then your upper layer is a clear or clarified oil. So if you want to use this oil in salad dressing and you put it in the fridge, you don't want it to cloud. The clouding comes from the presence of wax in your oil. So winterizing is often a process used to clarify your oil and remove the waxes. Again, we talked about mouthfeel, palatability, that has to do with melting and spreading of the oil, of the fat, for the mouthfeel. Safety, oftentimes we need to test the presence of secondary oxidative products like malonylaldehyde. So this is a secondary oxidative product from lipid oxidation, and it has adverse health effects, mainly cardiovascular. And cholesterol oxide is due to oxidation of cholesterol. It's something that we don't want to have present as well. So some markers for safety is looking at malonylaldehyde and cholesterol oxide, because oxidation is not only going to impact flavor, but it's also going to impact production of metabolites that are concern related to health. Okay, so with that in mind, with the importance of fat characterization in mind, we're going to look at different tests we use to characterize fat. So if we have different oils, fats and oils, we have analysis for bulk fats and oils that are used in cooking or in processing. Different types of oils, different types of fat that are used. And then we characterize them to determine some physical characteristics. I'll go over those in a bit. Iodine value, that gives us degree of unsaturation. It's an important test for characterization of the oil and also determining the efficiency of hydrogenation. So if we want to hydrogenate the oil and produce a saturated margarine from the oil, we need to determine if we really got all of the double bonds saturated with hydrogen. So we test iodine value before and after hydrogenation. Saponification value is an important characteristic that is unique for different types of oil, used for authentication purposes, identification purposes, and also it gives us an idea of the molecular weight of the fatty acids in these oils. So for example, if you have olive oil versus canola oil, you're going to have different saponification value that gives you an indication of the average molecular weight of the main fatty acid in these oils. Free fatty acids is used for different purposes: refinement, testing refinement of the oil, testing for hydrolytic rancidity, for example. And then we have methods to measure oxidation. Methods to measure the present state. That means here's the oil. Let's determine how much it's oxidized at this moment. Or evaluating stability. So that's for the shelf life, oxidative stability or hydrolytic rancidity over time. So we're going to talk about here in specific oxidative rancidity and evaluate the current state and shelf life. And then looking at fractions of the lipid, GC and thin layer chromatography to see how much cholesterol I have, how much monoacylglycerols I have, or diacylglycerols, or triglycerides, or phospholipids. So that would be analytical characterization of the different fractions of oil. Okay. You can ask questions. Why are you so quiet? Maybe I was talking fast and not breathing. Yeah, I'm going to breathe and let you ask questions if you have any. Yes.
Could you just look over the iodine value?
Yes. So the iodine value, actually, we're going to have a few slides on iodine value, but very quickly, the iodine reacts with double bonds. So it's a measure of degree of unsaturation. The higher the iodine value, the higher the degree of unsaturation of the oil. And it's used for oil characterization, differentiation between different oils. And also it can be used as a measure of determining if your hydrogenation process was complete. Also, it's an indirect measure of oxidation. Because when lipid oxidizes, also the oxygen attacks the double bond, so you'll get saturation. So if iodine value decreases over time, that's also an indication of oxidation. But we'll go over it more in detail. All right, so when we want to determine the status of the oil or the characteristics of oil or fat, we need to either, if we have a bulk fat and oil, so no extraction is needed. We're looking at, in the lab, you're going to be looking at lard, you're going to be looking at coconut oil, canola, olive oil, corn oil. So these are considered bulk fats or oils, and we don't need to extract. But if we're looking at an oxidation, lipid oxidation, let's say in a flour or in another food product that is high in fat, we need to extract the fat first. That's the first step that you need to do to determine the status of the fat or oil in your sample. So we use solvent extraction and then evaporate the solvent, and then you have your oil or fat from the food that you can determine the characteristics of that. Mostly we extract it to look at degree of oxidation. In sample preparation, if we are extracting the oil, for example, we have to be really careful to minimize heat, oxygen, and light exposure. So we don't want to cause oxidation during sample preparation. You don't want to skew your results by actually causing any change in the lipid fraction between when you start your sample prep to the time of testing. So you want to make sure you minimize any alteration of your fat. Did you catch everything, Sally? Yeah, I called Anya Sally today in the lab, just that you know. And Sally on Wednesday, I called her Anna. Okay. All right. So physical characteristics. So we have different methods for measuring physical characteristics of the oil. So, and these are mostly for identification and testing authentication. For example, refractive index and melting point. Different oils have very characteristic refractive index and melting point. So there is a table in your chapter in the book. I just have to figure out which chapter. This new edition, the newer edition, I don't know exactly the chapter numbers, chapter 23. There is a table that lists refractive index and melting point and other characteristics of the oil that you would need for the lab report, actually. I'm going to point you to that table now so you can write it down. Yeah, table 23.2 is a table that you're going to refer to, especially for iodine value or saponification value for the different oils we'll be testing in the lab. This table also has
Do we need to study this table or is it just?
No, you're not going to study this table. There's a lot of numbers. You're going to need this table to get the reported value of iodine and saponification value for the lab report. And I'm pointing it out also because in that table, you'll see refractive index and melting point. So different oils have characteristic refractive index and melting point. Refractive index correlates to the degree of saturation, for example. So, and they are used to identify, authenticate the oil. Smoke, flash, and fire point, these are important characteristics, especially when you want to use the oil for processing, heating, frying. So smoke point is the temperature at which the oil starts smoking. And then above that, sparks, above that, fire. And I do have a story about the fire. So I love frying food. I love fat, obviously. And I fry everything at home. So I always have a pan full of oil. And I wanted to make boiled eggs one time for my daughter. So instead of turning on the heat on the water, I turned on the heat on the oil. And I went down to work. And then I smell something. So I go up and actually the oil was on fire. So what do you think I did? A stupid thing. Yes, with my instant shock, I tell my daughter instead of leave, go out of the house, stay in the room and close the door, which is stupid, don't do that. When you're almost gonna burn the house down. And then I take the pot on fire and open the water. Explosion, obviously in my face, on the ceiling. I had to paint the entire kitchen after that. And of course, there's still fire. I take it, luckily there was snow outside. So I open the door, I throw the pot on the snow, and another explosion happened. I bet the neighbors think that I'm going crazy. I'm glad that there was snow. I don't know how I don't have a fire extinguisher at home, and I still don't have one, which is bad. Anyway, we don't deep fry with oils that have tendency to set on fire. And this is a test that we usually do for making sure that we don't exceed a certain temperature if we're using this oil for frying or heat processing. Cold and cloud test or point. This is done to check the degree or the success of winterizing. So remember, I told you winterization is done to remove, to clarify the oil by removing the waxes. And the cold test and the cloud test are basically similar. You just reduce the temperature of the oil and watch for cloudiness or sedimentation to determine how successful winterization step was. Solid to fat index, this is the relate and consistency and solubility, both are related to mouthfeel. And when we eat something fatty, how much we're gonna have a sensation of the melting in the mouth and the spreading in the mouth. It has to correlate with how much solid to liquid there is in our fat and how consistent and how much we can spread the fat. Usually consistency and spreadability are measured using texture analyzer. Okay, so these are our physical characteristics. Then we're going to spend time on iodine value, and you'll be doing that in the lab next week. So what you're going to do, each group, you're going to go back to the formation of groups. You go back to your group of 5, and you're going to be assigned a particular oil. Each group will be assigned an oil, and you will be determining the degree of unsaturation by running iodine value test. It's a very simple test. What you need to know when I ask you about iodine value in a test or a final exam, I would want to know, define the test and what it is used for. So what is it used for? It's a measure of degree of unsaturation. So this is important for you to know what iodine value does. And then when I say define it, so you define it as the grams of iodine absorbed by 100 grams of sample. So grams of iodine absorbed by 100 grams of samples. This is something that you want to remember. Now, how do we measure iodine value? So you have your oil, designated oil, corn, canola, olive oil, coconut oil, whatever it is. You react it with excess iodine chloride. The iodine chloride is going to go to the double bond and try to saturate the double bond. So the more double bonds you have, the less iodine chloride is going to be remaining, because we're starting with an excess amount of iodine chloride. The more unsaturation, the less iodine chloride I'm going to have. Okay, so you want to remember that. The remaining iodine chloride, I'm going to react it with potassium iodide to give me iodine. Okay, so the more polysaccharide, the more polyunsaturation you have, the less remaining you're going to get of iodine chloride, the less iodine that you're going to generate. So whatever iodine you're going to generate, you want to determine how much iodine you generated. So you use starch as your indicator. Here's the starch is used as an indicator. You add a couple of drops of starch, because starch and iodine are going to give you blue color. You titrate with sodium thiosulfate. You keep titrating to react with all of the iodine and get sodium iodide, and then you end up with colors. In this case, you're titrating to colors. So you start with blue, and you titrate until you have no color. So you do the hand up.
Understand the equation for iodine value is not almost the exact same equation as how you do the nitrogen value?
Yes, in this case, I was going to come to that. In this case, this is at equilibrium, the same way we derived the equation, yes, for nitrogen. It's the same way. It's based on equilibrium. You have the volume times the normality of sodium thiosulfate. And here you have the molecular weight of iodine. And this is the weight of your sample, because here you have to remember it's grams per 100 grams. So we divide by the weight of the sample and we multiply by 100 because it's 100 grams. Now, why do we divide by 1,000? Who remembers? Madison. Absolutely, because your volume here is in milliliters, and here you need your volume to be in liters. Okay, so liters always with the molarities and normality per liter of The unit is a liter per volume. So we divide by 1,000, then we get grams of iodine in 100 grams of sample. So we divide by that. Okay. The derivation of the equation is the same as we derived for nitrogen. Yes.
So the more unsaturated our fat is, the lower our iodine value will be.
No. Thank you, good question, but no, let's look at what we have here. We have blank minus sample, right? So the blank will have all of the ICL, nothing to react with. So all of the ICL will react with potassium iodide, will give you the maximum iodine possible. So the blank will have the highest volume. The sample, okay, if the sample is very unsaturated, polyunsaturated, you'll have a little bit of iodine generated. Your sample volume will be lower. So your iodine value will be higher. That was a good question. Did you catch all of that? Do you want me to repeat? Yes. What do you want? Yes, for repeating? Yeah, absolutely. Okay, so the blank will have the highest volume of titration. Why? Because all of your excess has nothing to react with here. So all of your ICL, that reagent that you add, all of it will react with the potassium iodide and give you the maximum iodine there is. Because nothing reacted with any double bonds. So the volume of titration will be the maximum because you have the highest iodine produced. So the volume here would be the highest for the blank. In the sample, if you have a very unsaturated sample, you're going to produce much less iodine, right? Because this ICL is going to react with all of the double bonds. So that you have less iodine chloride remaining, then you have less iodine here, then you need very low amount of volume to titrate. Therefore, here, the value will be bigger when you have more polyunsaturation. Therefore, iodine value is higher for polyunsaturated fat. Does that make sense? If not, tell me which step you want me to repeat. Very good. We'll go over that again in lab after Thanksgiving. Okay, but also always remember how we derived the equation. We derived the equation last time for proteins, right? Remember that. Because if you remember how the equation was derived, then you will know what to have when you are asked to calculate. And I promise there will be a question in the final on this. There you go. I'm telling you what the questions are. Okay, so you want to remember, if you remember grams per 100 grams, you know how to set up your equation. You know that, oh, I need to divide by 1,000, it's milliliter per liter. I need to divide by the weight and multiply by 100 because it's grams per 100 grams. I will give you the molecular weight of iodine, so you don't have to remember that. I will give you the normality of sodium thiosulfate, so you don't have to remember that. I'll give you the volume, so it's just a matter of plugging in and doing the calculation. And like I said, it's used for fat characterization, but at the same time, it's used for measuring the efficiency of hydrogenation and also an indirect measure of oxidation. The more the fat is oxidized, if you know that it is corn oil, you know what to expect in terms of iodine value, and then over shelf life, it was tested again, it was lower than some of the polyunsaturated fatty acids got ionized. Not ionized, sorry, oxidized. All right. Saponification value is another important test. And here, what is it used for? It's for identification. Bless you. It's for identification, and it gives you an index for average molecular weight of the triglycerides in the sample. So it's often used to determine the average molecular weight in your oil. And it is a measure of authentication, especially in olive oil that can get adulterated. You can do FAME analysis and determine adulteration, or you can do saponification value test, which is quicker than FAME, and determine if olive oil is adulterated. Okay, define. So what it is for and how you define it. Okay, so this is what it's for, and it's defined as milligrams of potassium hydroxide required to saponify 1 gram of samples. It's not 100 grams, it's 1 gram of sample. And it's milligrams, not grams. So milligrams of KOH, potassium hydroxide, required to saponify 1 gram of sample. Here's your triglycerides made up of 3 fatty acids and glycerol. And we saponify using excess amount of an alkali, in this case, potassium hydroxide. So in the lab, you're going to be putting the fat sample, adding KOH, putting it in a hot plate, and using the reflux system to heat it for about half an hour or so to ensure saponification. That means de-esterification. So you're going to free the glycerol, and you're going to produce the salt of the fatty acid, potassium salt of fatty acid. Again here, excess KOH. If you have a blank sample, no oil, your KOH, all of it, you would need to titrate it with HCl. So again, in this test, your blank has the highest volume of titration. Because here, if you don't have a sample, all of your base, you need to neutralize with the acid. So the volume of the blank will be greater than the volume of the sample, always. Now the sample, depending how big is, or how long is your fatty acid there, it reacts with the KOH that you have here in a certain amount of sample that you weigh. In 1 gram of sample, how many moles of the triglycerides you will have? The number of moles of triglyceride will be dependent on its molecular weight. Because remember, the number of moles is what? Is the molecular weight? Or how is it? I need to write it down to get the unit right so that I don't confuse you. So the molecular weight equals grams per number of moles, right? And then number of moles equals grams over molecular weight. Grams per mole. Okay. So if I have where I'm going with this. Okay. So just want you to remember molecular weight grams per number of moles. If I have very long fatty acid chains, I will have less moles per gram of fat. Does it make sense to you? If you have long, you will have high molecular weight, right? If we have long fatty acid chains, I will have high molecular weight. I will have less number of moles per 1 gram of fat. So remember that. Okay, does it make sense to you though? Because if you think of molecular weight grams per mole, and number of moles is grams over molecular weight. The larger is your molecular weight, the less number of moles I have per 1 gram of sample. Okay, that makes sense? True.
Do we use 3 moles of KOH because there's going to be
Yes.
3 moles
So
of fatty acids?
1 mole to 3 moles. That's very important observation, and it's important for the exercise we'll have next. because you have 3 fatty acids.
Yeah, and then one more.
1 mole to 3 moles will give you 1 glycerol, and you'll get 3 potassium salt of fatty acid, 3 fatty acids. Okay, so with that in mind, now we titrate the excess with HCl. We use phenolphthalein. In this case, I believe it's pink to colorless. I think it's pink in KOH, and then when you titrate, it goes to colorless. Everything I think in the lab is going to go from a color to colorless, except for fatty acid, 3 fatty acids, if I remember correctly. So here again, it's the blank minus the sample. Because if you don't have sample, you have all of the KOH, then you have the highest volume of HCl needed. When you have the more number of moles you have, the more volume the more number of moles you have, the less KOH you're going to have in excess or remaining, then the less is the volume of the sample. So if I look at this equation, 56.1 is the molecular weight of KOH. And the normality of HCl, and this would be in milliliters. You see here is only dividing by weight of the sample. There is no 1,000 at the bottom, and there is no 100 multiplied. Why? No 1,000 on the bottom and no multiplication by 100. Just a second, Dora. Yes, it's milligrams, not grams. So I don't need to correct milliliter to liter. And it's 1 gram of sample. So I only divide by the weight of the sample. I don't multiply by 100. So if you remember the definition, you will remember if you need 1,000, you need 100. So important thing is to remember the definition. Let's take some time to do math here. And I'll write down equations that helps you here.
Is this for extra credit?
Huh?
Is this for extra credit?
Yes, for extra credit. Pull out the piece of paper. You won't do this unless I say extra credit, huh?
No, I was just finding what's on the.
Yeah, there is extra credit plus 2. Take out your. All right. So what's given here is that your saponification value is 190 milligrams per 1 gram. So that is given. Your molecular weight of KOH is 56.1 grams per mole. Okay, so you have that. What else do you have given? Let's see. You probably need the molecular weight of glycerol, and you need the molecular weight of water. Molecular weight of H2O is 18 grams per mole. Molecular weight of glycerol is 92 grams per mole. So you will be given all of that in the test. You don't have to remember any of this. I will give you that. What you want to remember is 1 mole of triglyceride. You don't need to remember what happens in the chemical reaction, except you need to remember that 1 mole reacts with 3 moles of KOH. You don't have to draw the chemical structure or anything. You'll get glycerol plus 3 fatty acid salts. We don't care about here, okay? So 1 mole of triglyceride reacts with 3 KOH. We're looking at the average molecular weight of triglyceride, of the fatty acids. We first need to figure out the molecular weight of triglyceride. Okay, so 1 mole. So I'm looking at X grams per mole. I don't know that. That's the question. X grams per mole of triglyceride reacts with 3 moles of KOH. And you have 56 grams per mole. So you have 3 moles, you have 3 times that. So this is reacting with this. And the saponification value is 190 milligrams is needed for 1 gram. I need to convert that to grams in order to work with it with equiunits. So 0.19 grams reacted with 1 gram. How many grams in a mole here reacting with 3 times this many grams per mole? So it's basically cross multiplication. So I'm looking for the molecular weight of triglyceride. And I know the molecular weight of KOH. And I know that 1 mole reacts with 3 moles. How many grams per mole, that is the molecular weight? How many grams per mole I'm looking for here? And I know the saponification value is 0.19 grams reacts with 1 gram. By cross multiplication, I get this value. So basically, it is 1 gram times 3 times 56.1 grams per mole over 0.19 grams. So units cancel. And what is the value I get here? Anybody go that far? Huh? 885.79. Okay, I'm gonna just round that 2 grams per mole. Okay, so I have the molecular weight of triglyceride. Can anyone tell me how I can get the molecular weight of fatty acid if I have the molecular weight of triglycerides? Think about it for a minute. Do you have an answer?
Subtract the weight of the molecular weight of the glycerol.
Subtract the weight of glycerol and add what? Tyler.
Would you then divide by 3?
Before I divide by 3. So when you have 3 fatty acids reacting with glycerol, what do you generate?
I think we need to take the water into account.
3 moles of water. So because it's a condensation reaction, when you have triglycerides to form triglyceride, you have 3 fatty acids and glycerol. When they react together, they give you 3 moles of H2O. So you want to bring that back into your fatty acid calculation. Okay, so basically you want to remember that triglyceride plus 3 H2O under the right conditions, you need 3 moles of water for it to give you glycerol that is complete and 3 fatty acids that are complete. So triglyceride plus this will give you this plus that. So my triglycerides is 885.8 grams per mole plus 3 times 18. What's 3 times 18? 54. Okay, 54 grams per mole equal 92 grams per mole for glycerol plus 3 fatty acids. We're looking for the fatty acid. So I bring this over. So 885.8 plus 54 minus 92. All of that has a unit of grams per mole. Gives you 3 fatty acids. What's the value here?
847.
Okay, so 847 grams per mole. I'm going to divide that by 3 now to give me the fatty acid average molecular weight, Dora. 282. That is the average molecular weight of oleic acid. Exactly. Because the main fatty acid in olive oil is oleic acid. So if you look up the average molecular weight or the molecular weight of oleic acid, it's going to give you 282. So I have it all here, but without the units. Please make sure you have your units. Sometimes the units just crowd my slides, but you want to make sure you have your units so that when you have your units, they cancel. I don't want to be in the picture. Take a picture. Okay, great. So, any questions here? Do you get that? Yeah, Abby, we'll just make sure everybody gets that before the evening. Huh? Let's say that again. 3 moles of water, yes. No, it's 3. What equation? No. This is KOH. Don't KOH in the previous one. You are determining the excess KOH plus HCl. Forget, we're talking about this reaction. There is no water here. I'm just calculating the molecular weight, knowing that when I break it into fatty acid, water molecules will have to be distributed between glycerol and fatty acid. This is not the reaction happening here. This is my calculation to get the molecular weight, but this is not a reaction happening here. The reaction is this. Okay, all right, so yes. What's that? The 1 gram, it's here. It's defined as milligram of KOH equal to 751 gram. When I give you 190, means 190 milligrams needed to 751 gram. Yeah, good. So I'm gonna be here on Wednesday to lecture, but I understand some of you will be leaving town. I'm gonna open my Zoom. The Zoom is available and it's on my calendar. So if you go to my calendar and you go to Analysis lecture, you can access the Zoom if you're able to watch. If not, it will be recorded and it will be on Canvas, but there will be calculations still. Keep that page with you. Participate in the calculation, whether live or offline, and bring it to me on Monday after Thanksgiving. So for those that I won't see, happy Thanksgiving. Others, I'll see you on Wednesday.
What about the one from last week?
Huh?
The one from last week?
What was it?
Friday.
Oh, yeah. If you have the fiber calculation, give it to me today or on Wednesday. Just, I'm gonna stop recording. Otherwise, I'll just